In the previous video, we learned how if we look at our function and we look at its derivative, what it can tell you about is it can tell you whether or not your function is increasing or decreasing. So we sort of know if our function is going up or down. And today what we're going to focus on information that our second derivative tells us. And what our second derivative tells us is it tells us about how curvy our data is. So really the fancy word for curviness or curvature is going to be concavity. And so we're going to learn all kinds of things that our second derivative to tell us. So it's very important today to remember that we're always using the second derivative. So while you're watching this video today, what I want you to think about is the following question. So imagine that you're skydiving and the graph of your speed as a function of time from the time you jumped out of the plane to the time you achieved terminal velocity follows which one of the following? So it's important to note here that we don't want to think about our position as we jump out of the plane. That's a good place to start. You could draw that graph. But what we're really interested in instead is the graph of our speed. So which one of these descriptions matches our speed? So try to draw a picture now and come to it when you're done with the video. Try to draw it again and we'll talk about it in class. So let's start by looking graphically to try to estimate sort of this idea called concavity. So thinking way back to the first project of the semester, if we look at the blue graph up here of our function, what we can say is that for this region, so from as far left on our graph we can see until about, I'd say we should stop around 3 here. For this area, we would say that our function is concave down. It looks like an upside down bowl. And we can see that this matches up with our function of our first derivative here from 0 to 3 as well. That from 0 to 3 it matches up the same idea. And we want to notice something important, that the region on our graph that's concave down, has this upside down bowl shape, is the area where our first derivative seems to be decreasing. And since our first derivative is decreasing, what this tells us actually is that first derivative decreasing means that its slope is negative, so this means that our second derivative is negative over here for concave down. What we can do is we can do a similar thing and we can examine where is our graph concave up. So our graph will be concave up from here from say 3 to 5.5. So here we have that concave up, the nice bowl shape. We'll notice that our first derivative here is increasing during this time, and if your first derivative is increasing, what this means is that our second derivative must be positive because it has positive slope. So this is how we get from our function to our derivative graph down to our second derivative. So it's very important to note that we can say that our first function is concave up because our derivative is increasing, which means that our second derivative is positive. And this gives us our definition. So our exact definition will be that if we have a differentiable function on an open interval, we're going to say the graph is concave upward on that interval if our first derivative is increasing, and we're going to say it's concave downward on that interval if our first derivative is decreasing on that interval. Now the definition's fine, it's a good definition, however it can be difficult to use. So instead what we have is we have our theorem, which is called the test for concavity. So we start with a function whose second derivative exists on an open interval, and we have two key things that could happen. If your second derivative is positive, that means the graph is going to be concave upward, and if your second derivative is negative, that means the graph will be concave downward. Again, we want to think, well, what does this mean? So we work through the idea. Well, if the second derivative is positive, then that means f prime, our first derivative, is increasing. And that just follows from the fact that if you take a function and you take its derivative and you end up with positive, that means the slope of the original function, the f prime, is increasing. Okay, so what that means is positive slope, it's going up, and therefore what we have is by definition we have a concave upward function. And it's a very similar idea for the second part. Well, if the derivative of your derivative is negative, then f prime has negative slope, so f prime is decreasing. And this just follows from remembering what we mean about increasing and decreasing functions. So what we're going to do is we're going to use this previous test in order to find the concavity of the graph of the following functions. And so our function we're going to be looking at here is our function f. And what we're always going to be doing is we're always going to be looking at the second derivative of this function. In this section, the second derivative is very important. And I'm going to give some guidelines for finding where a function has concave upward or concave downward. And hopefully you see that these are very similar actually to figuring out where a function is increasing or decreasing with just one minor change. So the first step in our process is we want to find all points where the second derivative is 0 or does not exist. We do this because we know that if the second derivative is positive, it's concave upwards. If it's negative, it's concave downwards. Therefore, we need to look at places where it's 0 or does not exist. So we set our original function equal to 0, the second derivative that is. And we solve and we see that this factors pretty nicely. Let's see, so we get a 6x. We're left with x plus 2. So we get x equals 0 or x equals negative 2 as our places where it's 0. It exists everywhere. Step 2, we use these places we found in order to make intervals and then choose points on those intervals. So we can make a nice little table. So we've got ourselves intervals. So we've got our interval from negative infinity up to negative 2, negative 2 to 0, 0 to infinity, and we pick our favorite points on these intervals, so negative 3, negative 1, and 1. And hopefully you said now we need to test those points, and so we test them in our second derivative. So if we test negative 3 in our second derivative, we're going to end up with 18, which is positive. If we test negative 1 in our derivative, we end up with negative 6, which is negative. And finally, we can test 1 in our derivative. We end up with 18, which is positive. So what this tells me is where I'm concave upward or concave downward. So this means I went from concave up to down to up, and I can write this nicely. Concave down on the interval negative 2 to 0, and I would write concave up on negative infinity to negative 2, and also from 0 to infinity. And that's my final answer for where I'm concave up or concave down. Now, while usually it's not too difficult to sort of estimate areas where we're concave downwards or where we're concave upwards, it's hard sometimes to decide where do we actually change. Where do we change from this concave down shape to the concave up shape, especially if we're just going to look at a graph. So that's why we kind of want to do it algebraically to see what happens there. Now, two possible things can happen when concavity changes. The first one is that the tangent line at the point exists. So if we look at this graph here, what we can see is we can see concavity changes right around there, and we can draw ourselves a tangent line to the graph. My tangent line, of course, looks really bad, but that's what the tangent line looks like. It has the same slope as the point there, and it looks pretty nice. The issue is that what can also happen is we can also have concavity change on a graph very abruptly and have no tangent line. So if we look at the red graph over here, what we can see is we changed from a concave upward piece of graph to a concave downward graph, but we don't have a nice tangent line here. It didn't change in a nice smooth way. And we're going to give these places where it changes nicely a special name. They're going to be called points of inflection. So a point of inflection will, in your gut, what it should be is it should be a place where the concavity changes nicely, but we need to make sure we follow some technical rules. So first, we need to make sure the function is continuous at that point. So at this point we're going to call C. We need to make sure it has a tangent line at this point, and it will be called a point of inflection as long as the concavity changes there, okay? It has to go from concave up to concave down, or down to up. So I'm going to draw a few pictures of graphs here, and what I want you to do is take a minute to decide, does it seem like a point of inflection? Is it continuous? Does it have a tangent line? And do we actually change our concavity? So you should pause the video for a few seconds, look at each one of these, and decide whether or not it really is a point of inflection of the graph. So hopefully you've had a chance to look through them all. So we're going to concentrate on the first one up here, and we want to think, well, our graph seems continuous here, we have a tangent line, and we changed from concave down to concave up, therefore this is a point of inflection. In the second graph here, our function is certainly continuous. We can sort of draw through the point. It has a tangent line. It's horizontal, but that's a fine tangent line. The issue is we don't change concavity. We're concave up, and we're concave up, so this means it is not a point of inflection because it fails the third property. Down here in the corner, well, our function, it definitely changes concavity. We were concave up before, now we're concave down. However, it fails 1 and 2. It's not continuous, and it does not have a tangent line, so it's not a point of inflection. The third graph we have over here, this one also in fact will be a point of inflection. So what's going on here is we went from concave upward to concave downward. We have a vertical tangent line, but that's okay. Our function's still continuous, so therefore it is good to go. So there's one type of picture we haven't included here, and you need to do this bring it to class tomorrow. What I want you to do is try to draw a graph that satisfies properties 1 and 3, that is, it's continuous and concavity changes, but it does not have a tangent line. So try to draw this graph, and we'll talk about it in class tomorrow. So here we have a theorem that helps us find points of inflection. So it says that if you have a point of inflection on your graph, then what needs to happen is you need your second derivative to equal 0, or your second derivative does not exist. One of these two things must happen. Now the thing to note is that just because this happens, it does not mean it's a point of inflection. It doesn't guarantee it happens, but it means that these are good places to look at. These are good places to think about it could be a point of inflection. So this is the example that we did earlier, and what we found out in this case was we found that if we took the second derivative, and if we put in -2 we got 0, and if we put in 0 we got 0. So these are both good places to look. They could be points of inflection. However, we need to check a few things. First of all, we need to check, can we put this into the first derivative and get a tangent line? And as it turns out, you can for both of these. You're going to get tangent lines. And also, we also need to check, does the concavity change? And if we look at our previous example, yes indeed, the concavity changes here. So x equals -2 and x equals 0 are points of inflection. Now let's look at this example here of g of x equals x to the 4th. So if we take ourselves a first derivative, we end up with 4x cubed. If we take ourselves a second derivative, we end up with 12x squared. So the first step in finding concavity of this, is first we need to set this equal to 0. Well, if we have 12x squared, this just means that x equals 0. So this looks like it could be a point of inflection. Is this a point of inflection? It certainly satisfies that the second derivative is 0. But the next thing we need to do is we need to look at our test intervals from -infinity to 0 and from 0 to infinity. And let's pick convenient numbers, -1 and 1, and test them in our second derivative. So let's see, if we take our second derivative at -1, we end up with a positive number. If we take our second derivative at 1, we end up with a positive number. So this tells me that my function was concave up the whole time, So this means that x equals 0 is not a point of inflection because the concavity did not change. So it's very important to understand that just because your derivative or your second derivative is 0 does not mean it's going to be a point of inflection all the time. Just like back with first derivatives, just because your first derivative is 0 does not mean it's a relative max or min. Here, just because your second derivative is 0 does not guarantee you that you have a point of inflection. Now the second derivative can also be useful because it can also tell you not only about concavity, but also about maximums and minimums on our function. So our theorem says that if we have a function such that it has the first derivative equal to 0, and our second derivative exists, then what we can do is we can try to use the second derivative to see if it has a max or a min. So what this says is well, what you do is if your number that made your first derivative equal to 0 makes your second derivative positive, then you're going to have a relative minimum. If it makes your second derivative negative, you'll have a relative max. However, if your second derivative is equal to 0, well, your test fails and you have to try something else. It could be a max, could be a min. Probably need to go back and try that first derivative test. So let's take a look and see why this makes sense. So what we have is C is a point on our graph, and the first thing we want to look at is we know that if we put this in our first derivative, we're going to get 0. So that tells me on my graph here at C, I need to have a slope of 0. My tangent line is in red there. And what I can do is if I look at my test here, if my second derivative is positive, remember that that means my function is concave upwards. So second derivative positive means concave up. Well, let's look at my graph here. I have a concave upwards graph. I have that my slope is 0. I have a horizontal tangent line here at C. Well, that certainly does look like a relative min. It's a very similar idea to get relative maxes instead. It's because the second derivative negative means it's going to be just concave the other direction, which means it's going to be a maximum. Unfortunately, this test can fail. If the second derivative is equal to 0, it doesn't tell you anything, so you're going to have to try something else. But let's see how this might work in a problem. So let's look at a function here, h of t, given by t to the fourth minus 4t cubed plus 2. That's a very bad looking cubed there. And I've already taken its derivative and its second derivative to get us started. So the second derivative test says, well, the first thing you need to do is you need to figure out where your first derivative is equal to 0. So I'll start by setting 0 equal to my first derivative. And I'll try solving this. So this, let's see, this will factor, I can factor a 4 into t squared out. So I'm left with t minus 3, which tells me that my first derivative is 0 at t equals 0 and at t equals 3. So these are my points I want to check. And I want to check them in my second derivative. So I'll check my second derivative at 3. So I'll put 3 in here. So 12 times 3 squared minus 24 times 3. And I end up with 36, which is positive. So this tells me that my function is concave up. So by the second derivative test, I'm going to have myself a relative minimum at 3, and whatever I get when I put 3 back into my function. So this is good, the second derivative test works. Now I need to figure out what happens when I put in 0 into my second derivative, and this isn't looking very good, because what happens is I get 0. So here the problem is I'm in this third one, the test failed, I need to try something else. So I need to go back and try the first derivative test to see if I'm increasing on one side, decreasing on the other, or try to figure out something else that happens here. So most of the tests from this section were very similar to tests we'd previously seen. The key is that concavity and the second derivative test use the second derivative, whereas increasing and decreasing and the first derivative test use the first derivative. As always, try the problems that are posted online, post a question, take your quiz, and I'll see you in class tomorrow.